So I'll be presenting on some rather new work. We've been working on this for about 4 or 5 months, I would say, assessing the effects of source language on binary similarity tools. Quick introduction. If you don't know me, I'm a master's student in computer science here at KU. I actually just finished my undergrad last spring. I'm a year-round research and development intern at Sandia National Laboratories. I'll be joining their full-time staff also as a researcher in June. I work mostly in the system security, binary analysis, and vulnerability research space. I do similar work at Sandia as well as my research. So what we'll be looking at today, some background and motivation for this work, why we chose to do this. We have 2 studies to share. One of them actually is still kind of in the works, and we have recent data as early as Monday of this week. And then we'll wrap up and share some future work. And then I'm hoping to gather some feedback from the audience on some directions that we could possibly take this work in the future. So some background. I know a lot of people probably don't work on binary diffing. So what is it? Broadly, it is the process of comparing binary level code segments. So we're talking about binary here. We're saying compiled languages. So your C or C++. When you compile a binary, or when you compile a compiled language, it results in a binary to run on the target machine. So we want to compare 2 binaries to identify similarities and modifications. So different processes that we can use to do this. Graph isomorphism was one of the first techniques that BinDiff uses. Approximate nearest neighbor, more like a data science approach. And then there's a ton of machine learning research in this space as well. Features that we can look at: instruction mnemonics, move, add, compare, those sorts of things. Control and data flow information, as well as execution traces. So there is some work in the dynamic analysis space for binary diffing. So an example here, this is from BinDiff, one of the popular industry recognized tools. We have 2 binaries here. This is a single function. We see on the right side, the secondary binary. It looks to be that maybe a function was inlined. These are the sorts of things that would be interesting when performing binary diffing. And then if we zoom in a little bit, BinDiff also uses instruction mnemonics. So you can zoom in and say, oh, like this particular block, a whole set of instructions was completely removed. But these are the ones that look the same. And this is what we're interested in with diffing. So where is it applied? So my area of research is vulnerability research. So patch diffing is a big, widely used application. So what we do is say Microsoft, who their software is closed source, they say this particular bug was fixed in this new update. What you can do is you can pull the old version that had the bug and the new version that has been updated, compare them and see where that bug was fixed. Static library detection is another interesting use case. So take libc. You can statically link libc within your binary instead of dynamically linking it. You can find things like memset, memcopy, all your libc functions within your binary. Malware analysis is getting a lot of attention with binary diffing. So clustering certain families of malware together. And then again, static library detection. Intellectual property protection has seen some use cases, binary diffing. So seeing if some set of code was copied and then compiled into your binary, and then just general reverse engineering, like software understanding. So why look at source language? We're talking about binaries. Well, this guy. So C is in hundreds of binary similarity papers and publications. In fact, hundreds. I did a little search a few days ago, and there were hundreds of papers where all they use is C for their evaluation. In fact, the largest binary similarity benchmark that has, I think, like 15 million binaries in it, it's entirely C. So we really need to look at other languages. And oddly enough, there's a bunch that have animal mascots. So we need to just pick one right now. So we picked Rust. Love or hate it, Rust isn't going anywhere. We see it starting to emerge in Windows, the Linux kernel. Malware authors love it. Everywhere you look, that little orange crab guy is sticking its head around the corner. So Rust was the language that we chose. All right, so let's go on to our first study. We used bsim. So a little background on bsim. It is a extension shipped with Ghidra. So our friends at the NSA developed bsim and shipped it with Ghidra, I think 11. You can find it on GitHub, all the source code's there. It's really built for performant binary similarity. So if you're looking at corpus of thousands of binaries. You ingest a new sample and you want to see if it's similar to anything that you've seen before. That's what BSIM is really built to do. It's built on top of LSH, locality sensitive hashing. So really what BSIM is doing is approximate nearest neighbor search. And this is a very scalable approach. LSH was popularized in the NLP community. So Ghidra and BSIM are taking motivation from them. So we do need to give you a quick understanding of BSIM to understand our results. And this all resulted from, I would say, a month or two of source code analysis, because Ghidra and the NSA didn't publish anything besides like how to use BSIM. None of the underlying technology is really documented besides the fact that it uses LSH. So we did quite a bit of work to understand how it works. So BSIM uses P code, which is Ghidra's internal intermediate representation. So you lift the binary to P code in Ghidra as you would normally do. And then BSIM actually uses both control flow and data flow information. So the B in BSIM, as you saw on the last slide, stands for behavioral. So BSIM is trying to capture more information than just the structure of the binary. They're also trying to capture an approximation of the behavior of the binary. Things like variable sizes, opcodes, certain variable properties, like is this variable an input? Is this variable a return value? Is it global? Is it local? As well as the normal basic blocks, in degree, out degrees, edge types. Is this a true or false? Is this an outgoing call? Is the call a direct call? Is it an indirect call? All of this information is encoded inside of a BSIM feature. We have a quick example here. This is actually a combined feature. So the right picture in black, the left side of that is the control flow for this little code snippet. And then the right side is actually the data flow information. It's a bit small, but really what we see here is the result of the move into EAX is effectively compared with 0 with the test instruction. And then the result of that is used for the branching instruction to go either to the block 1 or block 2. So after collecting all of these features for a function level representation, features are actually encoded as 4-byte, not 8-byte like the slides say, but 4-byte hexadecimal values, and then they're stored in a vector that is called a signature. Do note that some features can be repeated. So here we have TF, which is short for term frequency. That feature is repeated 3 times within this function. So we gather up these signatures for every single function. So after features are gathered for every single function, they're stored according to LSH. BSIM uses an internal proprietary hashing algorithm so the goal of LSH is to put similar things together and put dissimilar things as far apart as possible. So they have a specific implementation of this that they use. Really what you need to know is like if a function is within a bin with other functions, it is seen as similar to BSIM. So when you query for a new function, what will happen is BSIM will run this hashing algorithm again. It then determine the bin that your function belongs in. And then it will only return those functions in that bin as similar to your function. You can configure to say, like, I only want the top result, I want the top 100 results, but the maximum that you can get is the number of functions in the bin that your function falls in. So BSIM uses 2 primary comparison metrics, similarity and confidence. We'll breeze over a lot of this for time, but what we need to know is that BSIM ships with a default weighting scheme. So what they did is from all the binaries that the NSA has available to them, they gathered the most popular features, the most commonly seen features, and then assigned them a probability or a weight score that is distributed with BSIM. So when we compare 2 functions, you get the weight for each of the features that you see, and then it's effectively a cosine similarity, a weighted cosine similarity to compare 2 functions. Then you have this really convoluted confidence score that uses a number of other probabilities that come with BSIM. So we put in our paper for this that although BSIM, its source code is distributed, the code for determining all these probabilities and all these weights is like nowhere to be found. There's no mention of them. They don't say how we got to that point. So you can read the paper if you're interested in looking at kind of what we've approximated to be these values, but no similarity and confidence. Okay, so now we're on to our experiment. So we gathered 8 different databases. vSim works on a database level. 4 for C-based binaries and 4 for Rust-based binaries. We use core utils as our experimentation case here. There's actually a Rust port for core utils that is meant to be like stand-in. So that's what we use. What we do is at each optimization level, we create one database. So in total, we have 8 databases. So there we have one database for C01, one database for C01, and then the same for Rust. We use a Ghidra script to get all the features for every single one of our binaries, and then query them on the database that matches with that binary. So if we are collecting features or performing our query for a function compiled at O0 for C, we query on the database populated from C binaries at optimization O0. That makes sense. So our first question was really just, is there an effect? Does this thing even exist? Does source language degrade binary similarity results? And if so, to what extent? So here we're recording accuracy, which is really just, is vSim returning the correct function? So we compile with all the debug symbols for our ground truth. And what we find is on the left side is C. We do see some degraded performance with C, but like when comparing O1 to O2, it's like 98% accurate, which is pretty solid. On the Rust side, we do see a degradation in results. So we go from 98% to 92%, for example, comparing O1 to O2. So there is some consistently lower accuracy rate demonstrated with our Rust data set. So that necessitated some additional questioning. So our second research question was, how does source language affect clustering-based binary similarity tools? So really what we'd expect from vSim is, even if a result had a low similarity, we would expect the correct result to have the highest similarity out of all of the results that it returned. That would be the expectation, correct? Well, it didn't really happen. So on the left side, again, we have C. On the right side, we have Rust. The O0 case is tricky because the O0 in Rust is effectively a debug build. So we would expect that there would be a great difference between O0 and O1. But if you look at the O1 to O2 and O1 to O3, those are our 1, 2, 3, 4th and 5th lines. On the Rust side, we see a number of our correct matches. So this is vSim returning the correct symbol, aren't the top similarity. So that's saying that vSim is telling us that there are matches better than the function itself. There are matches that look more like the function than the function itself, which is a confusing result. If you're a practitioner, like, this doesn't make any sense. And if you're a practitioner doing something like malware research, and you say that these two things are similar, this function is benign, the function that is matched is benign, but in fact it's malicious, that could be a confusing result. You could make assumptions that lead to a dangerous place. So we wanted to further partition out these results and see, okay, is similarity lower on average in Rust than C? We see the same thing. What's interesting again is the O1 to O3 and O1 to O2 results. We have correct matches returning anywhere from 0 to 50% similar. So these are saying that this is the correct function, but they're only 50% similar. They're only 40% similar, which was a concerning result for us. We're getting close on time. So our third question was, can features be tuned according to source language? Like I said, the code wasn't really distributed to do so. It's still an open question. We're pleading with the Ghidra team to open source this code. We did do a quick little study to see if the features collected from the Rust data set overlap with those most common features. We see on average that fewer of the features in Rust are seen in the C data set. And in fact, when they are seen, they're seen at a lower rate. So that's our occurrence score there. So the features that Ghidra and the features that the NSA team think are most representative of binaries seen in the wild today aren't really representative of Rust. 3 main takeaways from this study. Clearly, there's some effects, some degradation of quality of results due to source language. It's not really clear yet which features are most significantly affecting similarity, and then feature tuning should be explored when we have the appropriate tools to do so. So we're going to run through the BinDiff study real quick. It's 9:12. So what we wanted to do with BinDiff was start to answer the question of which features are causing this degradation in similarity scores. So BinDiff is helpful here because one, it's industry recognized. It's a Google tool, so people use it everywhere. But BinDiff only uses structural features. BinDiff doesn't look at the data flow that BSIM does. It's only looking at basic blocks and instruction mnemonics. So it'll help us discern if our structural features are the problem or if the data flow features are the problem. So a little bit on BinDiff, it's all documented, so I didn't want to go through as much of the technology background. But what it does is it uses this drill down strategy. So BinDiff has implemented a number of structural matching algorithms that are ranked from best result to worst result. What it does is if two basic blocks or two functions match at a high level, at a high quality, then that match is taken. If it doesn't, it tries like the next worst algorithm. Pretty simple to understand. It also uses similarity and confidence. So similarity is the weighted sum of the basically all the matched components of your binary. So the ratio of basic blocks matched, the ratio of functions matched, and the ratio of instructions matched. Confidence is the average quality of the algorithms that did the match. So this is really nice because we have a separation between similarity and confidence. They're not affecting each other. So we can use them as sort of substitutes for the sorts of questions that we're interested in answering. We use a similar setup, but BinDiff only does a file to file comparison, not a like one to many comparison. So we create one like BinDiff proprietary file format for every single binary in our data set. We use a similar workflow where we create a bin export file, which is the format that they use, and then essentially do a cross-product comparison. So like for every binary in our data set, it's compared to every other binary in our data set. So every O0 is compared to every O0, every O1, and so on. Okay, cool. So what we're really trying to understand is, does the structural representation of a Rust binary differ so significantly from C that would be the issue that we're seeing in our BSIM results? And for this, we use the similarity metric, because again, similarity is really just the ratio of number of things matched in binary A and number of things matched in binary B. What we see here, the orangish red color, depending on how you see it, is our Rust data set, and the blue is C. So we see again that the majority of our Rust results are towards the low similarity end. So we're seeing a higher degree of change between our Rust binaries that is quite different than we see in our C binaries. And each of these is, so this is O0 compared to O1, this is O0 compared to O2, and so on. So it's not as drastic in our higher optimization levels. So like there in O2 versus O3, most things are quite similar, but still we see a skew further to the left. So our second question was, do the structural changes of Rust binaries degrade the quality of matches? Here we use confidence as our like substitute metric here, because again, confidence is a average of the quality of the algorithm that did the match. So what we see here is that although BinDiff is able to match components in our Rust binaries, they're having to match with much lower quality algorithms. They're having to drill down much further than they're having to do with C. Again, in the O2 to O3 case, we do see pretty high confidence algorithms being used, but there is a slight skew to the left. Yeah, we're right at the end. So that's where we left off actually this week. We collected that data that I just showed was collected on Monday. So we're very much in the work in progress section. So we're actively working on this. BSIM, we're really waiting on the NSA folks to give us our tuning code. For BinDiff, the data is pretty new. A few questions that I'm interested in right now are, can we tune BSIM to a specific source language? The other source languages cause similarly poor results, so I'd like to look at Go. That's another language that's being used popularly in the malware space, especially. And then to what degree do the data flow features change? So similar to what we did with BinDiff, is there another tool that we can just look at data flow or possibly use an output from BSIM to say how much is data flow changing, to really get a grasp on like what features in Rust are changing so significantly that we see this decrease in quality. I think we're right at time. Cool. I gave that a version of that presentation for my interview at Sandia, and it took an hour and a half. So I'm glad we got through it in that time. Any questions?
The BSIM, you may
Yep.
have answered this in the beginning.
Yeah.
I missed it, but it sounded like there was a lot of high overhead just in terms of learning it, and then it doesn't have, you don't have access to
Yeah,
it.
yeah.
So why choose that tool? Was that the best for the job, or were there no other option?
Yeah, two things. So one, my research specifically, I'm really concerned with tools that are most available to practitioners. So in my role at Sandia, I kind of sit in a middle ground where I do some hands-on work and then I do some research to like feed into tools of the hands-on work that I do. So I'm really interested in what tools are available to practitioners right now and what do they need to know about them. So that necessitated like BSIM was a new thing that hadn't been documented. And then I was just curious about BSIM. Like I use Ghidra all the time, so I just wanted to know how it worked. Yep.
Is this something that you just use for malware detection, or you can also use it for like compiler optimization?
Yeah, actually, I think Professor Kulkarni has another student that used BSIM as sort of a measure of, because they were working on compiler optimization for ML compilers. So you certainly could use it for that, but you would need to do some kind of finagling of what your similarity metrics really mean. So like BSIM, for example, we have all these different features that are being combined into a single feature. So you'd have to parse out like, you know, if I'm optimizing a binary for performance, what does that look like in terms of BSIM's features, its feature set, whereas BinDiff is just structural changes. So you would have to think critically about what their feature set meant for your use case. But it's popularly used in vulnerability research, reverse engineering, malware, mostly. Yep.
Wondering, do these tools take like good obfuscation or adversarial inputs into account at all?
Yeah, so, and I was supposed to repeat the question. The question is, do these tools account for code obfuscation? So BinDiff has actually been shown to not handle obfuscation well, because most obfuscation techniques are structural changes, like control flow graph flattening is a popular one. BSIM actually in their documentation says that they attempt and have had decent results in handling deliberate obfuscation attempts. You know, I'm not going to speak directly to whether or not they've fully achieved that, but I think they use control flow quite a bit in their feature set, so I don't expect quality results. If that makes sense. Yeah. They attempt to. That's the behavioral in BSIM, but dynamic approaches do much better. Yep.
Any other question? Thank you.
Cool. Thank you, guys.